G'day, this is a video on definite integrals. The first one I made of this didn't work so well, but this one I think is going to work. So I think this might be the 11th video in the series on integration. And for this one, exercise 7.7, we're actually going to work out the actual area under a curve. In the previous video we looked at the proximate area under a curve using rectangles. This time we're actually going to work it out exactly. It's not too much different to doing normal integration. We've just got one more step to add into this. So I'm going to use this example here, x squared plus 1, and I'm going to work out the actual area between when x is 0 and when x is 4 for the function y equals x squared plus 1. And to do that you can use definite integrals. Let me just show you what area I'm actually going to work out, and therefore what I'm not going to work out as well. I'm going to put a line at here, x equals 4. I'm going to put a line at x equals 0. I'm going to work out the area bounded by those two I guess points there, this curve here, this x squared plus 1, and the x-axis here. So I'm going to work out all of that area under there. I'm not going to work out any area below the x-axis. I'm not going to work out any area above this curve here. Okay, I'm just going to work out that area in there. And you can see that often using rectangles might be appropriate, or even using a trapezium in this case might be appropriate as well. But if you want to get the actual area, you need to use definite integrals. So what I do is I set up the integration x squared plus 1 dx, but you'll notice here that I've got these two numbers here, 4 and 0. I call them terminals. I'm not sure if that's actually what they're called, but that's helpful for me. So I'm going to integrate this between the terminals of 4 and 0. 4 being the upper terminal, the furthest on the right, 0 being the lower terminal, the furthest on the left. And we can actually do that on the calculator, and I might just flick to that now just so that you can see. You push shift plus here, and you get these two terminals here. We've often ignored them in the past when we're doing integration, but now you know what they're for. So I'm going to put 0 and 4 here, and I'm going to put x squared plus 1 dx. Now I'm not going to push enter in a second. I'm going to just see if I get it right first using my hand method, and then we'll come back to that in a second. So I integrate it normally. I just get raise 1 to the power divided by the new power, x cubed over 3 plus x plus c. Now I'm going to talk about the plus c in a little bit, but at the moment I'll put it in there. And I'm going to integrate it. Now I'm going to put these square brackets around now to indicate that I have integrated this. That's what the square brackets mean, except I need to take into account the 4 and the 0. So I put the 4 up here and the 0 down here. Okay. Now what I do is I substitute 4 into this function, and I substitute 0 into this function, and then I subtract the 0 from the 4. This is a way of kind of addressing all of the the little rectangles underneath this, because I guess essentially what we're doing is we're adding up an infinite number of rectangles all along the way to get the actual answer. So I get this 4 cubed over 3 plus 4 plus c minus 0 cubed over 3 plus 0 plus c. And now I just simply collect like terms and subtract them. Now obviously 0 cubed over 3 is going to be 0, 0 is going to be 0, and then I've got this minus plus c. And this is what I was talking about before. Every single time that you do this with every single equation that you've got, every single integration, you're always going to get a plus c in this bracket here, and you're always going to get a minus c in this bracket over here, because you're always going to subtract them. So the c's will actually cancel themselves out. So back in 7.1 I think I said you have to have a plus c every single time, and that is true, but it just so happens in this case here, and in all of these kinds of cases, the plus c actually eliminates itself. Plus c minus c. So essentially with this you actually don't need to put the plus c in. Okay, you won't get it wrong if you do put it in, but for this you don't need to put the plus c, because it will always cancel itself out. And then I'm just left with 64 over 3 plus 4, which is 76 over 3. Let me just see if that's true here. 76 over 3, we've got it right. Well, at least our calculator and I agree. We might both be wrong, but we'll take the chance. Now, I'm just going to put this a little bit into perspective. 76 over 3 is approximately equal to 25.33 if I do the control equals thing. Now in the previous video I looked at when I was doing the left-hand rectangle method I got 18, and right-hand rectangle method I got 34. and the actual area is 25.33. So you can see that these are helpful, but this one's the actual answer, somewhere in the middle of those two. Okay. Now, a couple of properties that I want to go through before I finish. I won't do too many more examples of this because you've seen a lot of the integration before. It's just adding that one step of putting it in the big brackets with the 4 and the 0. So some properties are that you cannot get the area at a particular point. And the theory behind this is that you can't get the width of a point. A point doesn't actually have a width. I know kind of technically it does, but it doesn't in terms of area. So you can't get the area between A and A. That will always be 0. If you have the integration between 0 and 4, it is the same as between 0 and 2 plus 2 and 4. So if these two numbers here are the same, then you can actually split this integration up into the two different parts. There are some exceptions, and I'll have a look at that in the next video, or possibly the one after that. If it crosses the x-axis, then we can't do this anymore. We have to adjust it slightly. But it is true if it's all above the x-axis, or in fact all below the x-axis. So yeah, you can split them up, and the other way too is you can go from the right hand side, from this side to the left hand side, and sort of crunch them together. Except for the exceptions where it crosses the x-axis. Another thing too is that if you flip the terminals over, so instead of from B to A, you go from A to B, it actually makes the answer that you'll get negative, okay, which is really helpful in another part, which is probably coming up in the next video. But it's possible, but it's not really relevant right now. And I guess the other thing I want to say is that the old rules still apply. So you can split up the functions. So if you've got f of x plus g of x, you can do the integration of those two things separately, like this, if it helps you. Or if you've got them separately, you can put them together, depending on which one is easier for you to do. And the other one too is that you can always drag out a constant if there's a number in front of f of x, or even a letter that's not a variable. Then you can drag that out the front and do the integration like this, or vice versa. You can go that way as well. It just depends on whatever's easiest for you. So there you go. That's integration, like the actual area, the definite integrals as we call it, and hopefully that's made a little bit of sense and has been able to help you. And hopefully this video works, because I don't think the other one did. But thanks very much. Thanks for watching, and I'll see you again next time.